Hello and welcome to course P26. This is a resistance welding process, and this is basic process and power related to resistance welding process. To begin, let's take a look at all arc welding processes, which, by the way, this is not an arc welding process. However, it falls into one of the categories of our welding power sources we use commonly in fabrication. So all arc welding power sources, there's our heading. And underneath that, we have two types of power sources. And these are the ones in one shape or form or another that we use for all welding, whether you're welding nuclear to automotive to anything. Constant voltage process, it's all put up here in yellow. That is for wire feed process. Voltage plays an instrumental role in the pinching of the wire as it's coming out. Having that difference in voltage, that different type of voltage, it's very important to know because you have to treat things differently as you become more advanced in your welding. The constant voltage process also gives us pulses that we have to start dealing with. Now over here in the constant current processes that I've left in white, there's a bunch of other processes. If you're not familiar with them, they're common to the fabrication realm. We have shielded metal arc welding, which is your standard stick welding. Gas tungsten arc welding, we also know as TIG. Gas tungsten arc welding for aluminum and non-ferrous. Notice this is straight polarity and this one's AC. DC, AC. So there's a big difference between them. Carbon arc gouging, and of course, falling all the way down here is the resistance process. Now, I have a larger version of this that I used when I taught the apprenticeship program, and it's quite huge, but this is as much as you'd ever need to know for your average shop. If anybody has equipment outside of the realm of this, they could certainly let me know and I'd be able to help you out. So let's talk about the resistance welding itself. The proper name, and many people call it spot welding, right? But the proper name is resistance welding. You'll see it as RW. In some publications, I've seen it as RSW for resistance spot welding. Projection welding is one of the resistance processes. This is where you're commonly welding a component down, like a nut or a support or something like that, where you're using the resistance welding to take something and affix it. And the projections usually represent a part of the part you're welding down that has little points on it that we're going to melt into place. The resistance spot welding process is one of the most popular methods of resistance welding. Steel, aluminum, copper, silver, tin-based metals, all can be welded. I've had one chance or another throughout my career to weld all of these, and a lot of things that aren't even there, such as tantalum and titanium. So if you have any further questions, you want to get into this deeper, certainly let me know. Resistance welding replaces a lot, and it's very quick. It's beautiful for the automotive industry because most of the time we don't disturb the zinc coatings or the coatings as much as we regularly do with the gas metal process. So drilling, riveting, screwing, anything that takes 2 bolts or more, if we got to start putting bolts into things and screws, this is very quick. Now it's got something very good about it. It's really fast, and it's very stable as long as your joint is actually stable. There's some really good and easy processes to check it where we try to tear things apart. And if there's any problems, it's usually relatively easy to troubleshoot them and get them fixed up. The downside of this resistance welding process is it's very subject to the joint configuration. If the parts or stampings are changing, so will your resistance weld process, because we need to design our currents and the application of our currents to achieve resistance a certain way in order for stability to happen. And when those conditions change, so will our parameters. So you got to, just like the gas metal process for location, this process has to do with the joint configuration being able to close and being in good proximity and giving good access. So let's have a look at the resistance welding process through its cycle. We have here a few things. Let's have a look. We have a cap. And the cap is actually subject to a cold water. There's actually cold water coming down this tube and turning around and going back out. We have to keep these caps as cool as we possibly can for a bunch of reasons. First reason is, of course, it will start to crunch and munch if it overheats. And we need to keep this surface. If this surface changes, our parameters actually start to change. And that's another discussion for another time where we start to talk about steppers and tip dressers. So we've got a couple of tips here. Both of them are well exposed to the water that's being circulated behind them. Both of them would actually probably be pretty cold to the touch just a few seconds after welding as a result of this water flow. So what's going to happen here is this part's going to come into place. And once it comes into place, it's going to align itself the way we want it to. And then this gun's going to close and it's going to fire. So let's have a look. There's our plate. There's our contact. And there's our application of force until the time came that it was together and the force was at its maximum. Then we applied current for a certain period of time and shut it off. And then we held for a little bit of time afterward. Let's do that again. The plate, the application of force. Force is met. And we apply our current and we form something we refer to as a nugget. And of course, the nugget cools off. And then we have our weld. Hold times are usually just a few cycles. I mean, as I say, this is done very, very quickly, but this represents the way resistance welding is meant to be. We form the nugget, and by the way, if anybody thinks it's a button, the button is what gets torn later on. Just so we know right now. So that's the application. One more time: plate, contact, force, application of heat. Now remember that this force, how hard we're pushing up and down on this plate, has a tremendous effect on the resistance. And that's the whole idea here. The resistance is being modified by how much force we put on this. If I were to walk out and take an efficient process, here's an example. If I were to turn down the tip force in here, we would immediately start to see arcing, and possibly even expulsion, where we're going to get sparks that are going to come flying out of this. And that's a result of being both a poor contact and being poorly conductive. So we're not doing very well if we have a situation like that. So, resistance welding principles. Let's have a peek here for a second. Lapping of two or more pieces together. That's the first part that happens. So this is a document that kind of talks our way through what we just witnessed, okay? So lapping of two or more pieces together, clamping between two electrodes. A current is passed between the two electrodes. A molten pressurized capsule, right, is formed. And the current is stopped, but pressure is still applied until the spot weld solidifies. So we have to hold it to make sure that while it's in its plastic stage, it doesn't come apart. If it's in its plastic stage, we could get it could just under its own stresses, pull itself apart a little bit or even part ways. So we have to make sure we leave it there. The fused area is known as a resistant spot weld or a nugget. Here's a very typical machine. It's about as basic as it gets. Not everybody has a foot switch. Most of the time, especially in automotive, this is something that's done automatically. But in some of the smaller plants where you have low run and low volume, these machines are still around. Essentially, it shows you the electrodes and the throat, which is our clearance so we can get the component in. We got to have water lines going to, so there's water going to and from the guns. We've got a rocker arm and something to help us to apply pressure. This force is under such scrutiny. When it comes to the resistance welding process, you got to make sure that the force is correct every time. Hence, we have pressure gauges. And of course, we've got our heat regulator, which is our amp meter. And we got to have some sort of a water supply and a foot switch. Now, this is about as basic as it possibly gets. We can get these machines actually in a couple of different ways, and more than is listed here. But the very basics of them right now utilize an alternating current that gives you 60 hertz. Right, that's 60 cycles per second. Or we have something we refer to as a mid-frequency DC, which usually runs about 1,000 hertz. And you can actually time or set these ones up for milliseconds. You most likely, what everybody's getting now are mid-frequency DC, and it gives you a much finer control when you're dealing with milliseconds as opposed to dealing with 60 parts of a second instead of 1,000 parts in a second. 7 steps to the resistance welding development. The first one, as you can probably imagine from my opening, is to plan and design the joint. We need more than just two pieces of metal together. We need two pieces of metal that will stay together and be able to be held together. They have to be formed in such a way that across the electrodes, we have to be able to get that material together. Oftentimes, it's the resistance welding programmer that has to compensate for that. And how we do that is we actually run warm cycles. And that's a warm cycle is a cycle you put in before you weld that makes the material warm enough that it brings the joint together, and then you would fire the finishing weld. More about that later. Select the metal. Most of the time, it's pretty simple what we're doing with resistance welding. The easiest metals to weld, by the way, are the stainless steels or the nickel-based materials, or high nickel materials. Nickel is very resistant, so it absolutely loves resistance welding. I've personally seen 30 layers of material. There was 30 layers of material, thin, thick, all kinds, and it actually resistance welded right through the whole stack that we did at Bombardier years ago. Select the equipment based on a weld type. Is this a projection weld? Is this a resistance weld? How thick is it? How thin is it? We've got to select caps and everything too. The consumable size, like I said, we got to pick that size. The bigger the diameter, historically, the thicker the material. And we do that so we give the material an opportunity to have the maximized surface area, because larger current will start to blow it away even with the application of cooling. The internal cooling, it'll still blow a hole in if it gets to. We need a little bit of mass. Development procedure and validation. This is you pulling out the spec. We're going to pull out the spec sheet now, and we're going to have a look at that. And we're going to see what we have to do to validate and prove that this weld is good. Destructive testing is very common. To take one part and rip it apart is very common. Validation based on specifications, which I've already mentioned, and finalization of documents. You always have to, especially with the OEMs and the manufacturers, they want to know exactly how this is being welded. If anybody needs any sheets or anything like that to help to get their station set up, because each station should have some type of information on it to say where it's set today and where it is and where it was yesterday, if there was any changes made, who made them, all that kind of stuff. If anybody needs documentation, they can certainly get a hold of me, and I have things we can help to put you in place. So the resistance weld nomenclature, that is the development of all these different things, is we always get our contact area. The contact area is pretty good. The heat affected zone is always known as this area that's on the outside. Now we have to do some metallurgy here in a few minutes. And when we get to the metallurgical side of the presentation, then we're going to find out what we do. What are we doing to the material in the heat affected zones? Now, resistance welding people have historically never had to worry too much about that. And in fact, you can use resistance welding currents to get you some certain heat treatable characteristics for the material. For example, you can anneal your heat affected zone with some extra impulses. There's extra things you can do. So this is the basic contact area. This is the heat affected zone around the outside. And after you're done welding, it forms a nugget. Now, most of the time we're doing some level of destructive testing. So if we try to rip this off, we tear a button. So buttons are torn, nuggets are formed. Buttons are torn, nuggets are formed. So I always say to people, have a good look at this plate. Have a good look at when you rip one off and you tear a button. What does it look like in here? Is it really, really hard? Does it look like it broke? Or does it look like it's very ragged and tarry? Right? I'm very interested in always knowing what the heat affected zone looks like, because you could have a fantastic weld in this area and you could have a lot of brittleness in the other areas around it. And this brittleness will cause things to crack. So that's it for this part of the presentation. Thank you very much. As always, let me know if you need any further information. Thank you. Bye-bye.